Thanks, Gary, for always having my back. Thank you. I know it's been some tough love on chat sometimes. I could hardly contain myself yesterday when Lewis was up here saying the things that I've been saying about outcomes for 5 years. But it gets worse if you think about it, because what Lewis doesn't know is he doesn't know that we're actually, most of us still are measuring the outcome before the sealer's set with some sort of look. And he doesn't know about Strindberg criteria. He doesn't know about that. So it's actually as obvious as it was to him that we're not going about this correctly. He actually doesn't know the full depth and width of the problem. And what we need to begin to think about is how someone could look at our literature from outside our field and come to those conclusions so quickly that we've been missing for literally decades. And Gary kind of hinted at it, but really I'm not, what I'm teaching is what you hear David and Clark and I talk about, but what I talk about on chat is the process. It's the process, and we're trying to change the way people actually think, and the difficulty is that people naturally think this way when you talk about the weather, and I loved it when Goodman used the weather example and the coin flip example, because those are the exact examples I used last year. But then when we look at our scientific literature, we get it all jacked up, and we have this hodgepodge mismatch of stuff that we're using to evaluate our scientific literature. Let's do the lights down a little bit, Carlos. Okay. We're going to talk a little bit about, and the outside projectors are probably going to be the better projectors for the images when we get there, but I think the middle projectors will be fine for the title slides. We're going to talk about the image generation. I'm still seeing on TDO, I'm still seeing the same problems with understanding scattered radiation, beam hardening, and what I've been calling reconstruction artifact, but it's metal artifact. And these are distinct things, and they interact. And we're going to review that today. We're going to spend a pretty big chunk of time on that because we're imaging around all of these things, and it has dramatic impacts on what we're able to see, what we're actually able to see. Someone last year asked Birbaum, well, when are we going to get around that? And Birbaum's like, those are blind spots. I mean, it was that same kind of obviousness that that's not going to happen. Those are blind spots. And so we need to learn when this stuff's going to deceive us. So Gary asked me to review CBCT, image generation, reconstruction, artifacts, the role of uncertainty, tests and testing. I don't know how much we'll get to that because we still are having some problems with this part here. We'll try to pull everything together, talk about why serious people have taken this path, and you saw a couple of very serious people yesterday. Birbaum's satisfaction of search. Boy, if you guys haven't watched those videos, I had Birbaum as a mentor, so I really got lucky. It was just being in the right place at the right time with the right background. I'll talk about that just a tiny bit, but get those videos. I've watched them like 5 times, and I'm still picking up stuff. The guy he is so wide and deep. I'm going to talk about how to read a CBCT, hopefully talk about the design of perceptual experiments, and directions of logic. You heard about Goodman talk about that yesterday, and again, it was one of those things I could hardly contain myself when he talked about probability versus likelihood, the 2 directions of logic that we get messed up. And then maybe we'll get to how to read the literature also. But again, I said how to read a CBT, but we don't really know how to read a CBCT yet. If there's one thing that's pretty clear and compelling from the medical literature is that expertise, it's a decade of effortful study with mentoring and feedback. So I don't know how to read a CBCT. I'm going to show you how I go about reading a CBCT, and I hope that if I talk about this again in a year or 2, it's something different. So again, mostly where I'm at, it's not because I'm smarter than anybody else. I just got lucky. I was in the right place at the right time. I was at Iowa. Iowa just happened to be a hotbed of this research. Birbaum was there. P.J. Chang was there. Chuck Metz was in Chicago, and there was this big corridor that was happening between these two schools where all of this stuff was happening 20, 25 years ago. And I was there, and I had to write background, and I was interested in it. So this was just luck. I'm not smarter than anybody else in this room. I'm just ahead, and I'm only ahead because I got lucky. That's it. That's all there is to it. So that's what Gary said. It's what Gary meant when he said, I'm not smarter than anyone else in the room, but what I am is a lot less dumb, because I'm a little bit, just a little bit more tuned into when I'm likely to make these errors. Kahneman says he is this way too, but the minute that he steps out of his domain, he makes the same blunders that everybody makes, and I'm the exact same way. So in my domain, I kind of know when I'm going to make mistakes a little bit more. But once I'm outside of my domain, I make the same blunders that everybody else makes. So what we want to do is we want to develop a little bit more sophisticated understanding so that we don't make these kinds of mistakes that you see in some of the printed literature and whatnot. So understanding where the errors are made is every bit as important as every bit as important. So understanding where the errors are made. So there's a lot of pieces to this puzzle. We've got the literature, we've got the actual imaging piece, there's the eyeball physiological stuff that goes on, there's this perceptual stuff, cognitive stuff that all leads up to this interpretation task. And we've been focusing a lot on this part here because everything kind of sits on that. If we don't understand the image generation process, we're kind of done. And we roll into this image interpretation process with a sense of ease, and we mistake that cognitive ease for accuracy and how this stuff actually works. And this is really complicated stuff. Here's the book. If anybody wants a weekend of pain and suffering, you can try to read through the first chapter of it. So there are some problems with cone beam CT, and a lot of people don't understand that cone beam CT, actually although it goes around 360 degrees, the geometry of the device actually doesn't collect a complete data set, and the image that's generated is an approximation. It's not an accurate, it's not a full fidelity reconstruction. So there's some problems with cone beams. We're not going to talk about any of this stuff. It's just too painful. But
we have French people here, so let's talk up Laplace a little bit.
We'll get to in Fourier. But again, a key piece is approximate 3D reconstructions in cone beam geometry. Missing data in the 3D radon space. So while we see the patient go, the head go all the way around the patient, that actually doesn't collect a complete data set. The reconstruction technique is an approximation because there's missing data in the cone beam. And for us, the missing data piece is even worse. So we're going to talk about a few sections in this book. We have to talk about X-ray generation and what we're going to call photon-matter interaction. And then over here, we're going to talk about, I can't quite read my slide there. We're going to talk about beam hardening, metal artifacts, and what I'm calling reconstruction artifacts, and I'd really like us to try to use that language to distinguish it from scatter and beam hardening. You can see he has separate sections. These are different things. And then we're going to talk about scattered radiation artifacts. So these are the three artifacts that we're dealing with all the time, and we're getting them confused. And then we're going to actually talk about the reconstruction artifacts, we actually have to talk about the reconstructions, how those work. So this will be the focus of this part, is learning to understand these three types of artifacts that plague our images. Scattered radiation, beam hardening, and metal. These are three different things. Again, you can see it's got three separate text chapters, text sections on them. We're going to develop some better mental models using what I'm going to call a water analogy. We're going to develop some better mental models of how these things affect the image. So here, you can see that we've got this beautiful, crystal clear, still water, and we can see right down to the bottom, but we got a very pretty reflection on it as well. So we're going to develop these models based on kind of water, with water, how to better understand scatter, beam hardening, and reconstruction artifact. So later, maybe the second part, we're going to talk about some of these perceptual and cognitive issues, some of the Birbaum stuff as well. And then I hope to actually go through maybe one or two papers as well. If you got a cone beam, you got to buy this book. You got to buy this book. This was the book that pushed Gary over the edge. So I got him this book a couple of years ago, and you can see what's happened to him. So can you read the slides? Nah, not so good. Okay. I can point out the portions that I want at least. So here, there's a few sections. This section says perceptual factors in reading medical images, cognitive factors in reading images, satisfaction. These are separate chapters, by the way. Satisfaction of search in traditional radiographic imaging, the role of expertise in radiographic image interpretation, separate chapters on these topics. 1, 2, and then there's actually a third chapter on receiver operating characteristic, ROC, analysis. I didn't see a chapter on sensitivity and specificity. There isn't one. It's a very amateurish way of characterizing an imaging modality. There's 3 chapters on ROC. These are world-class guys, and this takes a while. There are labs that are set up. This is the lab at Iowa. Kevin's, I think, the head of that lab. This is another lab that's at Arizona. These 2 of the people, Elizabeth Krupinski and Seme, they wrote this book. And if you look at their background, Dr. Krupinski is a research professor at the University of Arizona in the Department of Radiology and Psychology. Kevin Burbaum, assistant professor in academic physician, Department of Psychology? What are psychologists doing in the Department of Radiology? Oh, there's perceptual and cognitive issues, so maybe we understand how the brain works, which is why I'm always bringing in Kahneman and Taleb and Shebris and Simone and all these cognitive science guys, because there's a huge cognitive part to what we're doing. So when I see this literature where we're drilling a hole in the bone and we're getting the cone beam lined up right on that slice where the hole in the bone is, and then we ask the observer, is there a burr hole in the bone? It's really amateurish. It's just not well done at all. And it's misleading. We actually know way back from the day that who's reading the radiograph? So this is really old stuff that we haven't paid attention to. Okay, so I go through that to show you that this area is really wide and really deep. And like Burbaum said last year, if you're going to do research in this area, get help. Get help. It's complicated. Again, that book, there's an entire chapter on the design of perceptual experiments, and that's followed by 3 chapters on ROC analysis. So these burr hole experiments are problematic. It's not burr hole defects that are the problems, it's how the research is designed that's the problem. The way to do this is to start digging. Gary told me, he says, if you don't get this stuff at first, it's okay. It's okay. You just start chipping away at it. A journey of 1,000 miles starts with 1 step. So you got to go again, and then you'll get a little more, and then again, and get a little more, and it's effortful. This isn't something you just read. This is something you kind of got to study, and you just chip away at it. And we're all in different places. Okay. So the traditional tasks cone beam people talk about with cone beams, you can look at any of these kinds of references, is tooth morphology, dental periapical podosis, root fracture, root resorption. So those are the kinds of things that we talk about. So Andy Sure puts this up. Andy, are you here? Andy didn't make it out. Good, I can make fun of him. Nishan's here. He's going to get made fun of too, though. So Andy puts this up just before the South Carolina meeting. And he says, where is it in here? Radiographic uncleanness is symptom-free. Recently, the RD attempted to retreat it, however, the scan shows some apical findings. I was able to remove the previous face fill. However, the canals were completely calcified below that. And he says, looks at the radiograph, and he sees what he thinks is a patent canal space. So I put patent canal space in quotes is appropriate, Andy. What was it that you really saw with the CBCT? So when Andy looks at this and he sees what looks like patent canal space, what is he actually seeing? What is that? Pardon? It's a finding, sure, it's a finding, but what is that finding a finding of? Yeah, what is a radiograph really? This goes right to the very base. What is a radiograph really a picture of? It's a picture of attenuation, density, close. And when you think about it in that way, I mean, this looks like a patent canal space to us, but the radiograph has no idea what a patent canal space is. It just knows how many photons hit it. And in that area, more photons hit it than hit it here. That's all it is. That could be, really fibrous connective tissue in there that doesn't attenuate. So a radiograph is kind of, in a way, it's a picture of metal. It's a better way to think about it. So we need to spend some time on understanding, to understand radiography and imaging and cone beams especially, we need to understand attenuation. So we're going to develop a better understanding of what attenuation means and how to think about it. So if you look at scattered radiation artifacts, attenuating anatomical objects such as a shoulder abdomen. If we look at his description of beam hardening, we can see the radiation attenuation. So these are key concepts. Understanding attenuation are key concepts to understanding these processes. Metal artifacts. One known problem in CT metal artifacts we consider low energy X-rays are attenuated more strongly than high energy X-rays. So if we don't understand attenuation, or what the radiograph is actually showing us, we're going to have a harder time understanding these things. We, in our head, have this kind of mental model of attenuation. It's kind of based on Beer's law, that if you take a light source and you shine it through something, it gets dimmer. And that's okay with regular radiography, but as we're going to see, it's not so okay with cone beam radiography. Okay? So there are some problems with this Beer-Lambert model that we got taught in chemistry class, and we're going to spend a lot of time not going through those summations. So matter and X-rays interact in a variety of ways. This is how we model X-ray matter interaction. There are interactions based on the wavelength of the X-ray, interactions based on the atomic number of the matter. There are interactions based on what we're going to call the mass density. You're going to understand this in just about 2 seconds. And then there's the typical way we think about it, which is thickness. If something's thick, it knocks the X-ray beam down more also. Okay? So attenuation, a key concept. So if something is really loud, you cover your ears, and that attenuates the noise. If something's really bright, you put on sunglasses, and that attenuates that X-ray beam. And of course, the atmosphere can attenuate things as well. So we've got, probably Antarctica in the sun, or the high altitude in the sun, and there's a lot of X-ray, and then we've got the sunset going through a lot of atmosphere. So where I live, we're at a little bit of elevation, and so we get a lot more of this portion of the sun's radiation getting through to us. So what's happening here is that the atmosphere is attenuating, it's knocking down the sun's light. So if you go up to Giuseppe's at 12,000 feet in Telluride, there's a lot of sunlight, a lot of UV up there. So you put sunglasses on, okay? And that attenuates the sunlight. There are some eyeball things that happen as well, and perceptual things that are going to play with how we see things when we think they're attenuated. So let's look at this. Let me jump down and see if this is actually going to work. Sorry. Yeah, so most of you guys have seen this. It looks like the middle one is imaging it better. And so you can see this what's called a step wedge here, and we could think of that as this is highly attenuating on this side, and this is not attenuating at all on this side, or either way that you want to think about it. But what your eyeball is doing is it's making this what? This side is what? And that side is, your eyeball is playing with those attenuation values, because if we actually look at what those numbers are there, that bar is the same color all the way across. And I can back it up, and you can't fix the way your eyeball sees that. It's like you didn't learn anything. There it is. So we look at a radiograph that has this distribution of grayscale values, and we think our eyeball is like a photon meter or a VCR, and it's really not at all. I mean, that's a pretty clear example of how that actually doesn't work correctly. It works for us, but we need to be conscious of that when we're interpreting images. And there's a lot of misunderstanding about this stuff as well. So I looked at this article on Wikipedia, and they talked about Mach bands. And then they used this dental example of Mach bands, and they said, an extreme example of Mach bands in a dental radiograph due to the high density of the arch wires is projected against the natural tooth. And I looked at that and I said, That's not a mock band. Who knows what that is? What is that? We talked about that last year. It's ringing artifact. It's ringing artifact. Now there may very well be some mock band there, but that's ringing artifact. So everybody see that this is whiter on this edge and it's darker on that edge? Can everybody see that? You can't not see that. You can't not see it. But if we actually do an attenuation profile and go across there and we draw a line across there, this is what it looks like. There's no bright spot there. It just goes straight across at the same gray level, goes down to the other gray level, and then straight across. And you can look at that and know in your head that that's what's happening, and you can't not see that it goes there, a little white, back down, a little dark, back up. And the same thing happens in a vertical orientation as well. So you can't almost not see those mock bands. So your eye makes stuff up. It makes stuff up. Now if we look at the dental radiograph, so there's no ringing there. If we look at the dental radiograph and we do an attenuation profile, we draw a line from here down to here, you're going to see across, down, up, overshoot, across, overshoot, down, back up, flat. That's ringing artifact. There may very well be some mock band there, but that's ringing artifact as well. So again, ringing artifact is something that happens with our regular dental radiographs that causes people to look at crowns and things like that and say, oh, the margin's open, those kinds of things. And we have more extreme examples of this with cone beam radiography. So again, this is this phantom that they used here, and you go across and it's this gray level, and then you hit this gray level and it steps up and then it's flat. I did image processing on this one in Photoshop, and then ba-dip, down, ba-dip, up, and then back, ringing artifact. This is an image processing effect. And again, more eyeball stuff. So if you look at this and you look at these two orange circles, they're different colors, right? Everybody's seen these before. Who hasn't seen these? They're so powerful because you can just connect the dots and then they're the same color. And then someone pointed out one time, they said, oh, you tricked us, you made the background different colors. No, the background's the same color too. And you can back that up and you can't not see that. So our eyes are not to be trusted. So when you see these kinds of things radiographically, you need to think, an alternative hypothesis might be that my eyes are lying to me about this. Finding that I think I'm seeing on the radiograph. And so even here with these glasses, we can all look at these glasses and we see the nose piece in there. And if we look at what we're going to call the density, how bright that is, this nose piece is actually a very different color than that nose piece, isn't it? From a computer standpoint, from a number standpoint. And if we look at her, we can see that she's going to see part of the light that goes through, part of that light is bouncing off as well. So part of the attenuation process is the beam gets knocked down and absorbed, and part of it is the beam gets bounced off and goes other places as well. So we got to remember that we've got our beer goggles on at all times. Okay? So, Andy, what is Andy seeing here? We're going to make this a real simple model at first. Andy's seeing here attenuation. And so this area here where it looks like there's a patent canal space, that is less attenuating. It's not knocking the beam down as much. And he said patent canal space in quotes because the mental model that we have is when there's a dark spot where there's a canal that's supposed to be there, our mental model is that's a patent canal space. But it's not a patent canal space. It's a patent canal space in quotes because we don't know what's in there. It could be a material that's not attenuating also. So that's a better mental model. We're going to spend some time on this. This is the reconstruction process here. So we're imaging an object, the patient. There's data acquisition, 360 degrees around. That results in an incomplete set. Glenn, you got a question?
Yeah, I'm just wondering what would have been a better way for Andy to phrase that?
Patent canal space in quotes. I don't know. You got a way?
No, I don't.
Yeah, I mean, that's what it looks like, but we need to divorce the assessment of that as a patent canal space from it actually being a patent canal space, because all we have is the radiodensity information.
So Heidi said it might be a patent canal space.
Suggestive of, perhaps, maybe, but it was none of those things. He couldn't get down it. He's skilled.
I refer to it as the phantom canal phenomenon.
Phantom canal phenomenon. We need better language because the language is a reflection of mental models. You've heard me say that over and over and over. And that's why I use quotes a lot of times, because I don't have a word for patent canal space in quotes. All I have is the idea that's kind of what we think that is, but that's not really what it is. It's just some abstraction. I don't know what to use for it. So we need people to think about this and come up with better language.
So John, just to clarify for them, the model that you can figure this out by, say, taking different views or looking at the axial slice and thereby figuring out whether it's an artifact or what kind of attenuation it is that a viable model or not? By changing angles, views, that sort of thing.
So can you slice around?
Exactly.
You can't slice around that stuff. We're gonna see. I've got some phantoms in the way that medical radiologists study this stuff. If you look at it, they have phantoms. They've got Shep-Logan phantoms, they've got contrast phantoms, they've got 3D phantoms, they've got all kinds of phantoms that they study and characterize their imaging systems with. They don't herd 1,000 patients in and image them and go, oh, you got vertical root fractures. That's not how it's done. So I got you've seen my bike, I've showed it for 2 years now. We're going to look at my bike in detail this time. So it's a nice little phantom because it's very simple for us to understand what does this look like in the real world, and what did the approximation look like? And there's a lot of steps that go through this. We're going to understand you cannot slice around some of these things. They are acquired, they happen at the time they're acquired. At the time they're acquired. I'm glad I'm doing this lecture again, Gary. Okay, so around...
I know most of you have seen this now, but isn't it more clear now than, say, it was 3 years ago? Yeah. Now this is starting to make sense, right? Yeah. It takes a while.
It takes a while. This is the actual smart guy down here. These are the smart guys. He's a German guy. He's in a lab, and I look at his stuff, and it's like, I don't even know what he's doing. They're developing metal artifact reconstruction routines using gamma, lambda interpolation, and the fourth polynomial, I don't even know what they're doing. But there are smart guys that are working on this stuff, and the internet's wonderful. You just got to read. You got to do a little homework. But this is how our FDK, what's called Feldkamp-Davis-Kress method, this is how our cone beams work. So we have the patient in here. We see the head go around. That X-ray head sprays the radiation through the patient. It's picked up with the detector. Those are our projections. Our projections, our mental models of what our projections are incorrect. We're going to go over those again. Those are filtered, and then back projected, and then the object is reconstructed, and this is an approximation. It is an approximate X-ray cone beam reconstruction algorithm, an approximation. We need to know when it's going to lie to us, or when it's more likely to lie to us. And part of that for us is understanding those three kinds of artifacts and how they interact. So attenuation, okay? So getting back to that, because this is at the core of understanding is our model is that the X-ray beam is here, the patient's in the middle, and the detector's here, and we shine that beam through them. And that beam is attenuated in a variety of ways. One of those ways is what we're going to call wavelength attenuation. So high energy, blue, purple, high energy X-rays go through everything. They're not attenuated, so it didn't get smaller. So this is how strong the beam is, and it's the same strength. A low energy, a red beam, see it's a longer wavelength. It just goes through soft tissue and it gets knocked down. It's a shorter beam, okay? Atomic number, okay? So, calcium, the X-ray beam can go through. We're made out of metal. Bones are metal. Calcium's a metal. Atomic number. Now, this relationship is a fourth power relationship, and this jacks everybody up. It jacks everybody up because we have a hard time thinking just in like squares and then cubes and then fourth power. So 5 squared is 5 cubed, oops, kachunkata. You can feel system 2 getting in. 5 to the 4th, system 2 is now fully engaged. 625. Okay, so the difference, if you double something, you increase the attenuation by like a factor of 16. It's dramatic. And this really hurts us in endodontics. Mass density, so you can have the same material, calcium, and you can have it in its cancellous form or its cortical form, and this is not going to attenuate very much. See, the beam is strong, it goes through the cancellous bone, it's still strong. Mass density, the cortical bone is much more dense, much more mass dense, so the beam is strong, goes through the cortical bone, and the beam is attenuated. Did I say this correctly? Beam strong, goes through the cancellous bone, it's not very attenuated. And then this is how we typically think of things, is thick and thin. It goes through the littler thing much easier than it goes through the thick thing. Okay, thick and thin. So attenuation. The beam gets knocked down in a variety of ways. Cubed relationship, fourth power relationship, linear relationship. Okay? What does that mean for us? What that means for us is if we take something, so this is my bike, and this is the axle, and this is a tiny bleb of mercury that's in the axle. And I can take the exposure and I can crank it up, and crank it up, and crank it up, and crank it up, and crank it up. How many photons got through here? None. None. You can't compensate for this. Okay? So again, attenuation, it's knocking something down. So you can think of it like sunglasses. And you put mercury over there, she's not seeing anything. Just doesn't get through. Okay, attenuation. Questions on attenuation? All right, what you see is a function of how it's illuminated. Now we're going to start to talk about beam hardening because we understand a little bit about attenuation. We had to understand attenuation to talk about beam hardening. What you see is a function of how it's illuminated. So if you take a regular light bulb and you run it through a prism, we get the rainbow spectrum of colors, same as the sun. Our X-ray tube head also sends out, we can't see it, so we think it's one color. But it's not. It's a spray of colors, just like a light bulb is. We're just not aware that there's a spray of colors. So back to what you see is a function of how it's illuminated. So if I take that white light and I shine it on the apple, now we're going to use reflection here instead of transmission, but the mental model is still good enough for our purposes. So the spray of light comes out here in a rainbow color, and the green bounces off that, and the red bounces off that, and then we see that red and green with our eye. But if I only illuminate that with green, I don't see the red, because there ain't no red. Do we have any divers in the room? I know Glenn, Balson. Yeah, we're going to get to that. That's the model we're going to use. Okay, so what beam hardening is beam hardening is the X-ray beam is changing color as it's getting used up. Okay, just like here, the sunlight that started out with this distribution of X-ray colors and light colors all the way from X-rays to hard UV to soft UV, I can't quite read over there, to middle UV, near UV, visible and IR. It started out with this spray of colors, and the atmosphere did what to the beam? It attenuated it, but it didn't attenuate it evenly, did it? Not all the colors got knocked down the same. This actually, thank good, or we wouldn't be here, softened the beam. So the beam got softer. So the atmosphere softens the beam of the sun, which is why astronauts have to have these, you can't be up there in space without some pretty serious vision protection, and they get exposed. For the divers, based on the colors that you see, divers, how is this person deep or not deep? Based on the colors, not what they're wearing. Not very. How do we know not very? Yeah, because Mark says the deeper you go, the loss of color increases. So this diver is not very deep. We know they're not very deep because you can see the bright reds on them. So we have the sun here, and the sun sprays out this set of colors, but as the water, so this is water down here, so this spray of colors hits the water, and look what happens to red. Red's knocked out. So that diver is not very deep because we can still see the red. As that diver goes deeper, the color goes away. So here, the beam was, so we had this, let's just say this is an even distribution of color up here. What happened to the beam, the color of light, the light beam as we go down in depth? Did it get softer or harder? It got harder, it got bluer, it got harder. We lost the low energy part of the beam. Okay, so the atmosphere softened the sun. The water hardens it. Now, of course, it gets dimmer too because it's getting attenuated, but the color shift changes. So this is a really clear example of what you see is a function of how it's illuminated. Joel Arthur Barker's got a book called Paradigms. He's got a little side tail, a little sidebar that he talks about with divers. And the diver comes up and he says, now, listening to his talk about paradigms, he says, now I understand why I get down on a deeper dive and I look at the Budweiser can and the red, white, and blue labels are the colors that I know them to be. And so he's looking at the Budweiser can and he knows what color he says, I could never understand why that would happen because I know at that depth I can't see red. Guess what his brain did? Filled in the red. And I've shown you guys that we just do that. Okay, so we want to be careful about that. So that's our beam hardening. Our beam hardening is as the beam goes deeper through water, it changes color. The beam changes color, and that changes what we can see. And if you don't have red down there, you can't see red. If there's no red light down there, you can't see red. Yeah? What beam hardening means is, good question. So the question is, what does beam hardening mean? And that's exactly what we're talking about right now. What beam hardening is that we have, let's just say that we start out with a beam that's composed of exactly the exact same color in visible light, from purple to red. It's a flat distribution. It doesn't have a hump in the middle. Okay, it's flat, just for argument's sake. A hardened beam loses the red end because the red end is not very penetrating. It loses it, and so the beam shifts to the blue, and the blue over-penetrates. Now with X-rays, that's what we're talking about, as we're talking about over-penetration. Because our X-ray tube head sends out a spray of radiation. What's the setting? It's kVp, it's kV peak, kilovolts peak. It's not kilovolts, it's kilovolts peak. And so there's a spread of radiation that's around that, a distribution, some at the peak, some higher energy than the peak, and some lower energy than the peak. What happens is the lower energy radiation gets knocked out really easily by filtration and by soft tissue and by hard tissue. And so what happens is the beam penetrates through the body or any material as this multicolored X-ray beam penetrates through. The lower energy photons, the red end of the X-ray beam spectrum, gets preferentially knocked down, which leaves the high energy portion of the beam still to penetrate through. What does that mean? It means it over-penetrates those areas. We're going to show some examples of what that is. Did that help? This is a pretty important concept, that the beam changes colors as it's getting used up. And that has effects because what's left to go through the next part of the structure is now a hotter beam. It's a harder beam, so it over-penetrates that structure. Yeah?
Are you then saying that they're the same dye photo? If they went deeper, that they would look completely blue?
You probably eventually wouldn't see them because the beam would get attenuated down to zero. But if there was enough light that would go down there, you would lose more and more colors. They'd probably look pretty blue. Or gray, actually. Yeah. Yeah, just gray, eventually. Yeah?
They look gray.
They look gray. Yeah, my divers say gray. But again, part of the reason they look gray is, what is our visual system's response to that end of the spectrum? It stinks. Well, our eyeballs have their own set of response that's not even. So we look at something, and we see down here, we see purple down here. But for us to see purple at the same intensity as we see a green, the purple has to be a lot brighter. I got a couple of laser pointers that I didn't bring, and the purple laser pointer is like 500 watts, and then I have a green laser pointer that's 100 watts, and the green you can hardly look at with your eyes, and the purple's kind of dim. And it's 5 times the power. So our eyeball response is different too, so that might be another reason why it just kind of looks gray, because we don't have that color discrimination down in that end of the spectrum that we have light. Another possible reason for it. You got it. That's exactly what beam hardening is. Yep. And we have filtration that we place on the X-ray tube head because there's spray that comes out of there that's 20 kilovolts that all it does is contribute to dose and doesn't penetrate, you know, even a nanometer into the skin. So that's why we have aluminum filtration. And smart guys are playing around with different kinds of filtration, with copper filtration and different thicknesses of aluminum filtration to try to get, what you really want is you want a single colored beam. But we don't get that. No one's figured that out yet, how to make an X-ray that's one color yet. So we get this spray. Good enough? Okay. All right, beam hardening. Okay. So back to our girl. Let me back up a couple of slides. Where is she? Now, I'll go forward. It'll be fine. We'll catch it in a second. Scattered radiation is a completely different phenomena. So if you remember the girl with the sunglasses, she might be in this slide. Let me see if she is. Yeah, good. Ah, yes, I put her in here. That's why I wanted her. So we have this idea that we take our X-ray beam, and because we can't see it, Kahneman, what you see is all there is. No. Because we have this idea that we take our X-ray beam and we shine it through the patient and we see the sensor light up or we see the image, we have this idea that that's what's happening. Well, that's not all that's happening. There's what's called scattered radiation too. And so if you shine the light on something that attenuates, for instance, her glasses, who noticed the sun reflecting off of her glasses? Well, that kind of, from the standpoint of her eyeball as the sensor or the detector, that light didn't get there. It didn't get absorbed by the sunglasses. It got reflected off. Did it get reflected off like a mirror? Well, no. If you look at it, it actually kind of sprayed out and scattered. So scattered radiation, when we talk about scattered radiation, we've got our X-ray source over here, and we've got our tooth, and we shine it through. And on our heads, we're thinking that what the detector sees, so X-ray source, tooth, detector, going around in a circle. We're thinking what the detector saw right here is a reflection of what the attenuation was from this point to this point. But there could very easily be an X-ray that went up this way, banged into something, bent, and landed in that detector cell. Is that a reflection of the actual attenuation at that spot? No. No. And it's a big problem with cone beam geometry because our detectors are area detectors. They're big. So they pick up all the scatter, which is why cone beam CT is inherently a low contrast imaging modality. Medical CTs, they use a much narrower strip or a single strip. They're getting wider now, but they have the same kinds of problems. When you have a big bucket, like a big area sensor, you collect a lot of rain, a lot of scatter. Scattered radiation is an X-ray that comes in, and this one here, let's take this guy right here, this top one. He should have gone and boom, and landed in that bin. Did he land in that bin? No. He banged into something that set him cattywampus. And if the detector element was up here, that detector element would see that photon and thought it come from over here, but it didn't. So what scattered radiation does is scattered radiation decreases our contrast. And it can have other interesting effects too. So if you have two teeth, for instance, like this, and you shine the beam through, what are we thinking this is now? What's this called? If we shine the teeth through and we see this dip here, there's more signal in the middle and this dip here. This is it's an attenuation profile. Okay, we have to start thinking about these this way. This is our. It's a lesion. It's an attenuation profile, and then we have this background of scatter. And as long as our attenuation profile, our real signal, is above the scattered signal, because there's just going to be junk that ends up on that detector that has nothing to do with what actually went through, we're going to get a decent signal out of it. But what happens when we go this way? We actually might over-attenuate the beam, and our scattered radiation might actually have a higher signal than our actual signal. So this is what people talk about when they talk about signal to noise. We've got some signal to noise here. Here our signal to noise is upside down. We can't distinguish it. does the detector know the difference between this photon from scatter and this photon down here that was attenuated? No. No. The detector knows 14 photons hit. That's it. Here's my contribution to the reconstruction of these 14 photons that hit me right here. And the reconstruction process, does the reconstruction process know that that's a scattered photon or attenuated? No. That whole thing is all propagated through the chain. So scatter is, we're going to develop a model of scatter. So what scatter does is scatter affects our contrast discrimination ability. So I peeled these off of the internet somewhere. Here's the site, the source for that. So this image here, this image to us looks contrasty because we don't know what we're looking at. But if you look at here, you can't see those internal structures. We're going to blow that up a little bit. I must not have done the build on that. Look at the internal structures here, and you can see there's a lot of internal structure and a lot of internal structure that you can't see here. So this is a high signal to noise and high contrast image, and this is a low contrast image, and this is the effect of scatter. I've got a set of images for us to look at scatter as well that are ours. So our model for scatter is there's crud in the water. So here we can see right through the water to the base. Very clear, and we have high contrast. We can see our structures very easily through the water. Here, we're losing our contrast discrimination ability because there's a little crud in the water. Now, the surface of the water is still clear, still smooth, and we got a nice reflection off of it. And here, where we're not going through too much water, we've got pretty good contrast discrimination ability. But as the water gets a little deeper, there's a little more crud in the water, and we get a little more scatter. Our contrast discrimination ability goes down. And here the water's pretty cruddy, and you can see it's very low contrast. So look at how crisp this image is in terms of contrast, the brights of the brights and the darks of the darks. A little less crisp, everything's kind of more evenly colored. And here it's fairly evenly colored. We've got no contrast discrimination ability out here at all. Got pretty good here. And as the scattered light increases, we lose our contrast discrimination ability. That's what scatter is. Scattered radiation is radiation that hits something, ended up somewhere else, and only contributes to noise and low quality in the image, just junk in the image. Questions on scatter? Good.
I have a question.
Yeah.
In conventional intraoral imaging, you control for scatter with, collimation and also increasing your source to object distance.
Yeah. That's kind of the opposite. So in conventional radiography, we help compensate for scatter with collimation and source to object distance.
And also increasing KVP, right?
Maybe, but we only have limited control over that. And you can't increase the KV enough. Scatter's a problem. And collimation and what I'm going to call reverse collimation on the detector side is having the detector look through a telescope helps. Because a photon, the premise is that the photon, raise your hand. Okay, the premise is the photon came from you to me. And if my field of view is like that, I can pick up photons from Gary all the way over to Carlos. But if I'm looking through a telescope, if there's like a tube in front of me, I can only see you. So that's another way to deal with it. The problem is, what's our beam geometry? What's the size of our imaging device? So what we have is we have a beam that sends out a very wide spray it's uncollimatable. The patient would need to be in Kansas for the beam to be parallel, for us to do the telescope, looking through the tube trick. So we can't really, those parameters for us are fixed. It's what we got dealt, and it's part of the process that we're just going to have to accept, which is why our images are our images. They're low contrast and they're noisy, and smart guys are working to fix that, but there's only so much you can do because of the fundamental geometry of the beam. It's a cone beam. It is not a collimated beam. It's a spray. And we have an area detector. And it's pretty hard to kind of make an area detector that, like, I don't know, I mean, imagine someone could figure out how to make it that, like, looks through a partial pyramid at the point source. But whew, tough stuff. We're stuck. That help?
Yes.
Okay.
I think that's why micro CTs are better, because they bump the KV up so much.
They're,
And the
yeah.
distance is smaller, so.
Yeah, Herb Branson's micro CT stuff, he uses a synchrotron at Berkeley that's up where like smart people are, and you go in there and there's Ziz things and fumes coming out and helium containers, and you go and it's all dark and there's lasers everywhere. If you haven't seen his facility up there at Berkeley, it's pretty cool. But that synchrotron, I think, is mega electron, millions of electron volts, mega electron volts to get the resolutions that he uses. Yeah? Pardon, Mark?
Is there an exponential relationship between the density of the object being observed and scattering attenuation?
Is there an exponential relationship between the density, the mass density, the atomic number density? I don't know if I would say it's an exponential relationship. It may very well be one. But what I can say is more dense things scatter more. Yeah, good enough? More dense things scatter more. So that's why you saw in that example that I showed him, he said hip, shoulder, pelvis. Those are dense objects, and they just tend to cause more scatter. And then what happens is if you're imaging someone, so you take Scott, you all know Scott Weed, right? Where are you, Scott? Good. So you take Scott and you line him up, and you go through Scott's shoulders, you shine a beam on this side, nothing's coming out of that side. Okay? Nothing's coming out. So that part of the whatever hit the detector there, that's mostly noise on that side. No, as it turns out, with cone beam geometry, there's a lot of noise. There's just a lot of scattered radiation with that particular geometry. So mass density affects scatter, atomic number affects scatter. I don't know the relationship, but it affects it. More dense objects scatter more. Good. So beam hardening. The beam changes color as it's getting used. It's as you go deeper in the water, you don't see the reds anymore. The beam's hardened. You lose some of your color discrimination. Some of the colors aren't represented correctly. I mean, the red's still there, right? You just can't see it because there's no red light to see it. Okay. Scatter, we lose our contrast discrimination ability because there's crud in the water. There's just crud. Okay. So scattered radiation, there's our model for that. Here's our mental model for our beam hardening. We already had our diver story. I look at that suit, bright colored wetsuits, and then the guy asks, question for you, what color does the red look like at depth? Of course, you can't see the red at depth. So here's what we're going to call our physics-based conclusions. We've got a multicolored light beam. The beam changes color as it's used. What's that? Beam hardening. The beam changes color as it's getting used. That's our beam hardening. We cannot penetrate the high atomic number materials like mercury and gold. We cannot get through those materials. No photons get through. So if there's a crown in the way, and the cone beam detector gets a couple of photons, where do those photons come from? Scatter. Scatter. So the reconstruction in that area is based on basically scatter. Scatter is significant in cone beam because of the geometry, and it's a two-dimensional detector. Okay. The next part's hard. To understand metal or reconstruction artifacts, it's tough. If you don't get the process the second or the third time, that's okay. I'm going to show you, we're going to develop some better mental models on how to recognize it as well, but understanding how it happens is actually helpful and useful. This idea of the string of Cephs that you see everybody show, it's really bad. It sets up really, really bad mental models. Because we see, when you push the button down on the 9000, you see the tooth with the crown go through, and you see the implant go through, and you just see that as like the white dot going across the screen. And that mental model is really poor for how these images are actually constructed. It's 9:30 now. Whew. Okay. All right. So here's the reconstruction process. And again, there will be a test later on.
Oh, good.
Camille sent me this one. So here's our test jig. Here's my downhill bike. And Glenn loaned me his Nomad now for 2 years. Thank you, Glenn. So we're going to take my bike axle here that's basically a little aluminum cylinder. This is what it looks like in cross-section. So everybody can mentally image what this should look like on a regular radiograph. We should see more attenuation here, less attenuation in the middle, more attenuation here as it goes through the edges of these things. And we're going to take and we're going to image this little guy right here. And you can see there's a little hole, and I can either put a little bleb of mercury in there, or I can leave the hole patent. So, and you can see here, as it's whipping around, you'll see the little black dot whip around as we spin the axle around. Everybody understand what this is? Let me back it up again. Okay, see the dot? Look at the middle screen. I think it'll show better. Is it showing better on the middle screen? Yeah, good. So as we're spinning the axle around, that's what's happening. What's actually happening with the imaging device is we've got our cone beam CT, we've got our area detector right here. So this is the cone beam point source. It's spraying through the head, and each row of the detector sees what the row of the detector saw, so to speak, how many photons hit that particular row. And if we look at this in a row-wise fashion, not in an area fashion, but in a row-wise way, what did this row see as this rotated around? Well, it saw bedip here, and then it moved a little, and it saw the next bedip, and then it moved a little, and it saw the next one. So what the row saw is this kind of sine wave pattern. That's what the row saw. We're going to develop this a little bit better. But this is what's the actual reconstruction is based on. Now, if this actually is a bleb of mercury, how many photons actually hit here? Scattered photons, effectively zero. No signal photons got there. So what is the reconstruction then based on if there are no photons here? Junk. This is a tear. So we see that little bleb of the crown go through the imaging, and we just see the white spot. What's happening is it's creating this huge tear through the image, and this has pretty dramatic effects. Okay, we want to think about our image a little bit different now, because there's a lot of math that's going to be performed on the image as well. And part of that math involves some pretty significant heavy-duty mathematical functions. So if we think of an image as a mathematical function, we can invert images, we can add them, we can subtract them. So this image here, if we take white minus this image, we get this inverted image. So we've got to think about images in a little bit of a different way. Some of those mathematical transforms are very, very counterintuitive. For instance, if we take this image here, everybody sees the netting in the baseball player, right? We can take this image and we can make a three-dimensional image out of it. What's this? That's the ball out there, and it creates a little bit of a spike in the image. So if we think of an image as a coordinate system, as a function of x and y with an output, this is a high number, this is a higher number, this is a low number. So for any given x and y, there's a number. So the image is actually a function. Okay, when we think of the image that way, that allows us to treat the image in very different mathematical ways, in human understandable form and in computer understandable form. And for cone beam CT, it's the computer understandable form that actually gets manipulated. The problem is when we have these spikes in the image from these white spots, they're very, very sensitive to manipulation. So take this baseball image, most of you guys have seen this before, and you can see the netting goes this way and this way. And if we look at this image very closely, we can see a spike, 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 and here, spike, spike, here. If we knock some of these spikes out, so just by going in there in Photoshop and putting a little spray can on those spikes, I can take the netting out. Really, really weird mathematical transformation. Now, this was a dozen spikes here. If I put one dozen air sprays here, if I put one air spray in the wrong spot, I get a really weird image. So the processing of these images does not happen in a linear way that's necessarily really predictable for us to understand as a human. Okay? Here I can go and put spray here, and I can knock out just the horizontal netting. It's just the way the mathematical transformations work here. Okay, so the two things you just guys learned was the radon transform and the Fourier transform for our French-speaking people in the audience. So it's, again, thinking about the images in a different way. So back to our bike axle again. So everybody understand what they're looking at here. Here's the thickness of the wall. Here's the lumen of the axle. Here's the thickness of the wall. Here's the mercury bleb in the middle. And we're going to look at this in a row-wise way, and we're going to twist the axle around. And again, we're doing all of this work so we have a better understanding of what metal artifact and reconstruction artifact looks like. It's not as easy to understand or explain as scattered radiation and beam hardening. So if we take this image here and we do what's called an attenuation profile on that image, what's that going to look like? It's going to go through the wall. It's going to come up through the wall. Here's our mercury bleb right here. This is the lumen of the axle here and here. And here's the other wall down here. We're going to take that and we're going to call that 0 degrees. So everybody see the little mercury bleb in the middle? And that's our image at 0 degrees. And then we're going to take that image, that's our radon transform. We're going to take that image and we're going to put that over here with the Fourier transform at 0 degrees. So we're going to do that mathematical transformation that I did with the baseball players that resulted in the little spikes that we air sprayed out the spikes. We're going to do that weird mathematical transformation and we're going to put that transformed little line profile, that attenuation profile, at 0. Now I'm going to take the axle and I'm going to rotate it to 45 degrees. And you can see the mercury bleb is a little bit smeared out. We're going to rotate to 44 degrees. We're going to take that line out. That's our 44 degree line. We're going to do the Fourier. We're going to put that over here, and that's our 44 degree line. 90, same thing. So it's way over here at the edge, and it's really smeared out. So now we're looking at the mercury bleb is on the side of the axle, basically, as we're spinning it around. And that goes at 90. We're going to go to 185, just past our initial, because if I went to 180, exactly 180, it would be right on top of the 0 degree. So we're going to go just past it to 185. So you can see we're beginning to assemble a roundish space that's composed of the attenuation profiles that were transformed in a mathematical way over here. We're going to do one at 275. This is 3/4 of the way around. So we're skipping a lot, is what we're doing right now. And then another one at 355 degrees around. So we've got 1, 2, 3, 4, 5, 6 projections on this image. How many projections do you need? There's a 7th projection. How many projections do you need to reconstruct the image? So I got this slide from this guy's website here. So here is 5 projections of this. There's 10, there's 30, and you can see the artifact that's happening around these. So this is the object. What's this called? The reconstruction, the approximation. It's not this, it's an approximation of this. This is something that's really important to keep in your head. It's an approximation. So the more slices we have, the better we can do our reconstruction. That's pretty clear. And it makes intuitive sense, too. So let's go spin this whole thing around, all the way around, fill out the whole space. And so that whole space now, it's that spiky kind of look. So you can see the bright spike in the middle. There's one going off here, another one going off here. It's got some rings around it. So it's that spiky kind of look that we saw with the baseball players. Then what we do is we do another complicated mathematical transformation, and that gets us our reconstruction. So this is the reconstructed slice of this right here in this area. So it's not exactly what this looks like, but it's an approximation of it. Okay, so this is called central slice theorem. That's the inverse Fourier transform. So if we look at the bird here, we can actually see him as he gets reconstructed. So here's the unfiltered reconstruction. Here's the filtered reconstruction. You can maybe see the head and the wing and a couple of feet. And as we let that play a little more, as we let that play a little bit more, the reconstruction gets better and better and better and better and boom, pretty much done. I got this off YouTube as well. Okay, pretty cool. Now something to notice here is, again, there's some artifact coming off. So this is an unfiltered image. This is the filtered image here. There's some artifact on that bird. This bird here is an approximation of this bird here. Approximation. Not quite there.
John,
Yeah.
that's all software.
That's all software. That's all smart guy software
Is that
stuff.
gonna be manipulatable in the
Well, when you figure out how to get the photon through that mercury, then we can make it better. We're stuck. Pardon? Yeah. There's those tears in that image that occur. We see that dot of that crown that goes across, and it creates that huge tear. What actual data is in that tear? Junk. How do you do the reconstruction on junk? Well, you make it up. And smart guys have figured out better and better ways to make it up. Is made up data ever really going to be as good data? Remember yesterday Lewis was talking about imputing? It's made up data. It's never as good. You need the outcome. How many photons actually hit there that really count? Yeah. So smart people are working on better ways to do this. This is a very active area of research. Last I Googled it, there's like 300 PubMed articles. So here it is. This is all the pieces of the puzzle together again. It spins around, we get this tear in the sinogram, that creates this image here, and this is transformed to this image. It's a very complicated mathematical process, and that's all you really need to understand, is it's not linear, it's not even close to being linear. So, why did we have to go through all that pain and suffering? Well, we had to understand the matter and how the matter and the X-rays interacted so that we could understand we can't get X-ray photons through mercury blebs and gold crowns. We can't get that through because it's just the way that it works. This is a fourth power relationship. It just doesn't go through. And so what happens is if you have this gold crown in there, you see that little gold crown go through, but what it really is doing is it's creating this big tear in this image, and there's no data there. That tear in the image then has really weird consequences when we do these complicated mathematical transformations on the image. And we get some ringing artifact that happens as well, because those mathematical transformations are based on sines and cosines, and there's overshoot and undershoot like the ringing artifact we talked about. And so you take a regular periapical radiograph like that, and you do a cone beam reconstruction, and it looks like that, because it's an approximation of reality. So back to better mental models with metal or reconstruction artifacts. Again, image as a function. What mathematical function do you guys see here? Sine wave, up, down, up, down. As it turns out, those mathematical functions that I showed you with the baseball players, those are all Fourier based. They're basically sine wave, actually cosine, wave transformations of the image. So a better way to think about that is to incorporate in your head, as you're looking at these images, that these images have gone through some sort of wave transformations. The image was acquired, was manipulated, it was converted to wave form, and there's going to be some artifact from that conversion to wave form, just like the ringing artifact was. Okay? So just like the ringing artifact, the baseball player, he gets converted to wave form. And in wave form, if you think about it, there's a frequency to that netting. There's a frequency to the waves of that netting, and we can describe those mathematically. So if you think of the image from space, if we took this image here and we went across it like that, and this was our attenuation profile in space, our attenuation profile, and we converted that as a sum of a bunch of frequencies of different waves, that would be this image here. So this image is a frequency conversion of this image, and we can go knock out very specific frequencies of the image and take the netting out. It's a very weird transformation, but all of our cone beam images go through this transformation, and there's a problem with that. What's the frequency of a straight vertical edge? It's infinity. There's no frequency there. How do you go from 0 or no mercury to mercury instantly? Like all of a sudden there's like no mercury, no mercury, no mercury. Because it attenuates so heavily, it's got such a hard edge. We can't describe it in frequency space. It's made up. We don't have enough frequencies, high enough frequencies to do it. So what happens is we get some artifact from that frequency space, and when weird frequencies are absent or present, we can have just one tiny dot that wrecks the whole image. Okay? So this mental model is a bad one. It's not the way you want to think about the images. A better way to think about our cone beam images when there are highly attenuating materials in the beam, like gutta percha and posts and crowns, all those kinds of things, is that some sort of dimple or ripple is created in the image. So here's our little water strider here, and he creates these little ripples and dimples in the image. So you can see all of these ripples and dimples from his little feet, they're all interacting. All the little waves that are created from his little feet are interacting, and they're spreading out on the surface, on the plane of the surface of the water. So here's our little water strider. Here he is right here. Now we're looking through the water at the bottom. Is this scattering water or not scattering water? Not scattering water. We can see right down to the surface really clearly. But what we can see is we can see how the light from the surface gets all bent out of shape, and we have some blind spots that are caused by these little dimples on his feet. And these blind spots can interact in weird ways at a distance away from where his feet are. So here's his feet. He's in this area. Let's say 1, 2, 3 feet we can see, and there's a 4th foot that's over here. It creates these blind spots here, but also the ripples and interaction from his feet create other kinds of weird ripples and interactions at a distance away from the feet. So it affects everything that's on the plane of the surface of the water. Those dimples do. So highly attenuating objects like fillings and crowns create dimples in the plane, ripples in the plane that affect every single thing in the plane. They cannot be, they're part of the acquisition, they cannot be reconstructed around. So we look at an image and we think that we're actually looking at the image, and we're really actually looking at a reflection of the image. And if we have very still water and there's no ripples and there's no dimples, we can get a really, really beautiful reflection. And it can be hard to tell which is the actual image and which is the reflection. Can anybody really tell here? I actually don't even remember if this one's right side up or upside down. So we look at the image here, and if there's little ripples in the water, we don't get quite so accurate of a reflection because there's those little ripples and dimples in the water from the heavy metals. Okay? So here, what's going on with this image? This is one of my chair sides. Any guesses?
Usually.
Well, the case is short, so. What's going on? Nope. They didn't move. They were still.
Got an earring on.
She's got 2 earrings on. She's got 2 earrings on. Okay? So here's our earring spray. There's one earring that's probably about here, and we can see the spray coming from it. Use your imagination a little bit, and you can see that there's kind of a divergent spray coming from that side, and then another divergent spray coming from that side. Look at what the surface rendering looks like. Do we really think her bone is rippled and wavy like that? If you use your imagination a little bit, just following along here, this particular vein, we can see white, dark, wave, up, down, up, down. That's a direct consequence of the interaction of the X-ray beam with her metal earrings, creating this spray that affected everything in that plane. Because the images are reconstructed using waves, using sines and cosines, it has a wave manifestation in the image. Okay, so this was a couple of earrings. So if we look at this up here, look at this pattern right in here. Doesn't this look exactly like the water strider? Look at the way those waves are interacting. You can't slice around this stuff. It's part of the acquisition process because those tears in the sinogram create these little ripples and dimples in that plane, the surface plane of the water, and those affect every single thing in that plane. You can't get around it. You can't slice this way or that way to get around this type of artifact. So, if she's got earrings on, those earrings affect everything that's in that cone beam path of that image, which is why it was all the way through that whole image, because it was the whole vertical height of the image the earrings were. Okay? So if you've got a dental implant here, and you're imaging over here, this dental implant, and this more carefully, this crown is going to affect basically everything that's in this box that I'm outlining right here. And that whole complex is going to affect every single image that you go anywhere in that area. It probably won't affect the mandibular anterior teeth. But it could, this maxillary implant, if their teeth are close together, could actually affect the posterior mandible if they're far enough apart and the cone beam geometry is correct. So highly attenuating materials create dimples in the plane. Those dimples create little wave artifacts, and those wave artifacts can show up at a distance away from where the source of the problem actually is. So we see these crowns go through. So here's a jaw section here. There's a couple of crowns going through. This crown here is going to affect everything from about this height here to about this height here. Down below it, it's not affected, but it affects everything in its plane, in the plane that it's in. So here's 4 crowns in this tooth. You should see them go by again. There's 1, 2, 3, 4. There's the 4th one right there. So let's look at that image. I can put essentially an arbitrary number of fractures to kick my. No, we're good. I can put essentially an arbitrary number of fractures in there by just throwing crowns in there. So here's 1 crown artifact, another crown crack artifact, a 3rd one, and a 4th one. If you look here, you can see this kind of wave nature. See the wave nature? You got to tune your eye to look for it. Everybody see that? Good. Okay, and it's caused by these tears that are this is called a sinogram, these tears that are in the image. So 4 crowns, that one creates that spray, that one creates that spray, that one creates that spray, and that one creates that spray. You saw them all go by. So, metal artifacts. Think of these as ripples or waves in the surface of the water. Metal creates little dimples in the surface of the water that creates wave artifact, and those multiple waves can interact at some distance away from where the original wave was. Okay. So I see a project like this, accuracy of cone beam tomography, periapical radiography, and detecting small periapical lesions. And then they show a picture like this of the jaw section, and it's sitting in a tub of water, and they make a point. In a clinical situation, the presence of soft tissue results in natural radiation attenuation and scattering. To simulate this effect, CBCT scans were captured while the block sections were submerged in water. How much sense does that make? I mean, to actually go to that trouble to point that out when the major things that are going to affect the reconstruction process are the base of the skull, the spine, the crown that's across the arch, all of those kinds of things. So what do you think they were thinking of here? 2-dimensional radiography. They were simulating 2-dimensional radiography, and cone beam's nothing like that. So do you see how we bring our understanding of 2D radiography to the 3D task, and it's a problem. We make some pretty basic blunders in experimental design. The water there did nothing. In fact, I would be surprised if these rods here didn't attenuate more. And if you take a scan empty, you can actually pick up the rods and the bite plate, the plastic bite plate. The cone beam will actually see those kinds of things. Yeah?
If I heard you right, the crown on the opposite side of the arch is going to create that distortion.
Reconstruction artifact. Keep going.
Minus any crowns in the area of view, the arch, the other side of the arch, the crown is going to create a distortion in that view.
The short answer is yes. Here's the long answer. Let's go back and look at Monica. Do you see anything other than a tiny bit of gutta percha here that would create that dramatic of an artifact in the field of view? These are earrings. They're not even in her mouth. And they create a dramatic reconstruction artifact. So again, you see the mandible section in the tub of water and you go, oh. Because it's such a 2-dimensional way of thinking of things, and the tube head is going around the patient, and everything that's between that tube head and the sensor is in the path of the beam and affects the image. So we look at our cone beam reconstructions like with a 9000, and we're looking at a small area, but there are things that are outside of that area that are not in the field of view that affect the image in the field of view, but it's worse than that.
So a better model would have been to put a head, an actual human head.
To do it in a head or have something else around it, a skull or something like that. Or just, just not bother with the water, and certainly not make a point of bothering with the water as if that was actually going to do something, that you were actually modeling something of clinical importance. You just kind of made your life dirty because now you got slippery, nasty, stinky jaw sections. So I see that, that's the kinds of things that I look at and I go, oh, what were they thinking? So again, to say it again, things that are outside of the field of view, like the earrings, they're not part of what the image is, the acquired image here. They're outside of the field of view. They can affect things in the field of view because they are in the path of the beam. So this is when I say, be the beam. What did you go through as the beam to get to the detector? Okay, that help? Yeah, in the back.
So you had a heavily restored tube, and it's in the field of view. Are you going to have the ringing artifact, the scatter,
Reconstruction artifact.
and the reconstruction? Are you going to have all four at the same time?
You can have, the ringing artifact is just kind of a model of how, when we transform something in the sine wave, we get the overshoot and undershoot. And that's with regular radiography. Regular radiography. For cone beam, we can have that certainly, but the artifacts I want to focus on are scatter, beam hardening, and reconstruction. And they all interact. And I've got some examples that we'll call up to show you those. Good enough, Trudeau? Yeah, and there was another one in the back too, I thought. Okay, yeah.
So in this way, instead of turning 360 degrees, turning to 180 degrees, trying to eliminate this kind of out.
Okay.
That would be nice.
So Carlos suggests that maybe instead of going 360, you go 180. And actually, as it turns out, you actually want to go 360. And I really think our 9000, based on some experiments that I do, is really a 180 machine, half and half. You want to go 360 because you simply get more photons and you get more slices. So to do FDK, the style of reconstruction, the technique, the algorithm that's used that we've kind of skimmed through, this is skimmed through here, you need 180 to do it. So you saw 5 angles, 10 angles, and 30 angles. And 180 is basically a requirement for the algorithm to work. You saw the bird, and all of a sudden the bird popped up when it got all the way around. What 360 does for you is it gets you more photons. What does more photons do for us? Increases our signal to noise. So we get a better image if we actually go 360. So 180 is basically a requirement for the algorithm to work. It will work with less than that, just not real well. So 180 is a requirement for it to work. 360 is better. But again, there's nothing you can do, 180, 360, 270, 720, there's nothing you can do with our geometry to get around that. It's a fundamental problem of the way the X-ray beam interacts with the heavy metals, and photons don't get through. It creates that tear. There's no data there. There's only junk, only noise, only scatter there. And the reconstruction has to figure out what the data would have looked like. And there are sophisticated algorithms to do that. So smart people, again, are working on that. But we don't have any solution to that problem until we either change algorithms, someone figures out another way to do it, and there actually are other ways to do it. Till we change algorithms, or we figure out how to get a photon to go through an amalgam. We're stuck. That's Birbaum's. He's like, well, those are blind spots. That's it. Next. Yep. Yep.
John?
Yeah.
You know, with a pencil beam, the view from angle 0 and the angle 180 is the same. But with a cone beam,
It's not. I didn't even want to go there. Yeah, that's actually, remember I put at the beginning, the key problem of cone beam geometry is, so Scott, we can touch on that a little bit, but I'm the X-ray source here, and that's the object that I'm imaging. It's not in the plane, so I'm not imaging down here, but I'm imaging, because the X-ray is a point source, and some of the things that we're imaging are above it, and some of the things we're imaging are below it. I can't see what the top of that chandelier looks like. I can't go 360 degrees around and see it. That's the missing data. We don't have that data. So even the data set that we're gathering with cone beam geometry is incomplete, and that's a key problem of cone beam geometry, that FDK figured a workaround, an approximation to kind of make a best guess as to what the top of that chandelier looks like. You can't see it. Missing data. Okay. Wow, Gary. So, models. Models. What do we have here? Perfect reconstruction. No highly attenuating objects. No scatter. No beam hardening because we're not going that deep. We've got a perfect reflection. Perfect reflection. What do we have here? We have a little scatter, and if you look closely, you can see there's some little ripples. What are our little ripples? That's our reconstruction artifact. So we can see here there's not quite so many ripples, and we get a cleaner reconstruction. Here, there's more ripples. Okay? So we have these little dipples or rimples in the water that affect things at a distance away. Here we have more ripples. We have some scatter. There's certainly some beam hardening, which is why it looks that color. And here we have a mess. You can't see anything. You don't get a reflection, and you can't see through it either. Okay? So occasionally you get the perfect storm when the beams come together. A couple of waves come together, you get a real big splash.
Looks like fun.
Okay, let's do some cases. So, we're going to do my axial phantom first, and we're going to learn to identify some of the things that are in there. And then I think we're going to do a jaw phantom. It's 10 o'clock. I don't know where the time goes.
No, it's okay.
This was important. Okay. So here's our jaw section here. All right. So, what are we seeing? Remember, this is our aluminum axle. This is aluminum. What's out here? Air, right? Air? What's in here? Wait a minute. What color is this air? Why is this air a different color? It's aluminum. Photons went through. Why is this air a different color in here? Beam's hardened. We've just identified beam hardening. So this is the likely cause of why air out here and air in here is a different color. Beam hardening from aluminum. Beam hardening, okay? What's all this junk out here? Why is it not even? Scatter. Scatter, okay? What's this? Out here, here, all the way through in that plane. There's our mercury bleb. It created a rip through the whole thing. Everything that's in that plane got affected. See the whole, if you look carefully, if you're not paying attention, you'll just go right down through there and you won't even notice that the whole image got dark. You can see it in this plane, but in the axial slice, it's actually, you almost don't even notice it, but you can see the whole axial slice got darker. There's probably some ringing artifact there as well, but this is, what is this? All the way, this whole mess that's out here in this plane. Tear in the sinogram, that is reconstruction artifact. Reconstruction artifact. So they're all three here, and they're interacting. Now, let's zoom in a little bit. Let's focus a little bit of attention. So, describe the radio density of the axle as we go around. It's fairly even. Agreed? Yeah. Okay. Let's go down. Now we look at this. Why is this darker here? Here. And it's lighter here. There's probably some reconstruction artifact, but what did that beam have to go through to get to this spot? It had to go through the mercury too, so it didn't have to go through all of it maybe. Maybe it just nicked it a little bit. So this is actually some beam hardening here too. So in this one image, we've got really clear beam hardening inside, outside. We've got scatter all the way around. We've got reconstruction artifact here going through the plane. So our beam hardening is what we're going to call more of a mass effect. I mean, it's basically everywhere in that pipe, right? Our reconstruction artifact only is affecting what the stuff that was in the plane of the mercury bleb. And the mercury bleb can actually harden the beam, and that resulted in over-penetration because we had a hotter beam in this area here, and that's why this is dark in this area and it's lighter in this area. So all three things are happening. So Trudeau, what do you think? Pardon? You can get all three, and they interact. Let's do a case. All right. So here's my jaw section here. Do I need to show a picture of the jaw section? Okay. So let's go down, and we can see the crack in the tooth, right? Everybody see that? Okay. So what did the beam go through there? It's a NiTi file, but we can call it gutta percha. But it's basically the same radio density as gutta percha. Fair enough? Yeah? But what did the beam go through? It went through the whole length of the enamel, this impacted wisdom tooth, the enamel on the wisdom tooth, the length of the mandible, all the way. Did the beam go through a lot? Yeah. What did the beam go through in this direction? Not so much. Not so much. Yeah. So what we have here is, this is pretty cool. This is kind of hard to set this thing up at this angle, but I was bored one Saturday. So you can see the crack. Everybody see the yellow plane, right? Think of that axial plane that's you haven't tipped. That's what the beam saw. What the beam saw. So the beam saw the wisdom tooth, all that dentin, all that enamel, all that bone, the NiTi file. It saw all of that, and the beam is, what's happening to the beam as it's going here? It's getting hardened and attenuated, both. Okay? So as we follow that slice down, we can see that it's cracked, it's cracked, it's cracked, it's cracked, it's cracked, it's cracked. And the minute that we get below that enamel, there's no crack anymore. So what happened there was, remember when I did the two teeth and we rotated it and there was the two dimples and then the one big dimple? What happened here was the beam got hardened to the point where most of the reconstruction was based on junk and noise, and then there was some reconstruction artifact of it. Okay? So this is beam hardening and scatter and reconstruction artifact all acting up at once on us. Because the minute that we get enough beam back, the beam's not quite so hardened and there's more of it, the artifact goes away. Now it's even more interesting when we go coronal, because we've got a pretty good artifact here, and then there's this really narrow window where we're above the crown and below the amalgam. And yeah, there's some artifact there. There is some artifact. But it's not nearly as bad as the minute that we get to the amalgam, bam, everything heads south on us. So in this we've got a pretty good crack going here, because we're going through that enamel and that wisdom tooth and the length of the mandible. But the minute that we get above it, we don't have quite so bad of a crack as one might think, because there's more beam. The beam is only going through, it's not going through that wisdom tooth and all of that enamel back there, and it's not actually going through as much bone because we're above the bone too. But the minute that we get to the base of that amalgam, all hell breaks loose again. Making sense? Okay? These things all interact. Now, can you see cracks on the second molar? Okay, I can see them too. Those cracks actually are present. Those are real cracks. And they have, if we look at those cracks, so you can see cracks with the cone beam, but you can't reliably image how much metal is right there in that spot. Not so much. It's pretty clean there. Let's go look at this in curved slicing. Okay, so there's not much metal there. Now, this metal can affect this. It can. So you want to keep that in your hypothesis space. But there's not much metal there. So you actually can see cracks with the cone beam. You just can't predictably and reliably see them around highly attenuating objects. So there's kind of an organic nature if we look at these things. They don't look reconstruction-y. And again, if you think about what the beam went through, well, what did the beam go through here? Well, it really didn't go through anything to get to this point, this spot right here. Here the beam, in this direction, the direction of this crack, the beam went through all of that stuff. So reconstruction artifact is a far more likely explanation for this crack because it had to go through all of this stuff. Is it starting to land some now? Yeah? I can't see it, like he said yesterday, I can't see in the audience, so I don't know if there's questions. So if there are, just wave. Yes?
Do teeth from the other side, round, whatever comes from the other side, when you see in that field, that will have an effect?
Yes, it does. Next example. Yes, the answer is yes. Again, what the beam went through is everything the beam went through. It went through the neck. It went through the base of the skull. It went through the teeth and the dental implants on the other side of the arch. It went through the earrings. That's what the beam went through to get from the point source to the detector. That's why I'm almost belaboring this point. I'm belaboring this point because it's a key point, and we've had several questions on this now. Can stuff that's across the arch affect the image that you see, the reconstructed field of view? The answer is an unequivocal yes. Here it is, right here. So I looked at this image. This is from Monday. I looked at this image. Who did this cone beam? Barbie, Trishi, Annalicia, who did this one? We took a pan on her too that did not get copied over into TDO, by the way. Yeah. So do you see the wavish nature out here? Up, down, up, down, up, down, up, down. So I looked at this image and I said, girls, what did I say? Who did this case with me? Barbie, what did I say? I said, get a pan because there's a dental implant over here. There's a dental implant over here. And it created this reconstruction artifact here. So let's take a look at, because we don't have a ton of time left. 10:15, right? Gary? Yeah. Ugh. Let's take a look at this case, and I'm going to show you how I read a cone beam CT. So the first thing I do is we go to curved slicing. We go to curved slicing because this view is something that we can, what I'm going to say, grok. We can gestalt it. We can look at it and kind of get it because it represents something that we have some familiarity with. Now, we don't want to mistake the ease and the familiarity for our accuracy with this because this is a different image. And then also, this whole thing fits in our field of view as well, okay? So when we look at this image, the first thing that we do as an endodontist is we look at the problem, right? You don't want to do that. You want to look away from the problem. Birbaum talked last year with the contrast studies in the abdomen that if there's something that you're doing that's task specific, like looking at the gutta percha in the tooth, that's going to distract you away from your ability to detect other things. So what I do, knowing that, is I get the image so that it fits in my field of view. It's not too zoomed in. And I look everywhere but where I'm interested in. So I'm interested in this tooth. So I'll go through curved slicing, and everybody see the wave artifact here? This is from the dental implant that's across the arch. And I'll just go right through the curved slicing, and I'm just kind of looking for anything weird. And I'm not like looking for something weird, but I'm looking for something weird. Just kind of scanning through it to see is there anything weird going on. And to me, it just doesn't look like there's a lot weird going on. I'll actually skip over the tooth that she's here for, because I don't want to focus attention on that right now. And so I'm just kind of scouting or screening. Looking for findings around this tooth. No findings around that tooth. Now I'll go back and look at the tooth that I'm interested in. Okay, and I'll spend a little time on that. And so what I've done here is because normally Kodak will pop up in the new version of the software, you actually have some choices to default tab at launch. You can choose curved slicing at launch. So I'll choose that. That's my default now, is that it comes up in curved slicing at launch. And so it'll come up in curved slicing, and then it looks like this. What I'll do then is I'll go, again, I'll make my section thickness about 20 millimeters and draw my curve in there. So I get something that's like a pseudo-periapical, kind of pseudo-panoramic-ish radiograph that shows me basically most of the tissue densities and most of the tissue thickness. And I can go up and down and make sure that the jaw section fits within my reconstruction frame. Everybody get that? Okay? This is a quick check. Jordan can go over all of this. Jordan, are you in here? Good. Jordan can go over all of this. But I feel very strongly that you should go to curved slicing first. Go to curved slicing first. Make a thick section and kind of grok the image. And try not to look where you're trying to look. Look away from there first. On the maxilla, I'll look at the sinuses first, and then I'll look at all the other teeth, and then maybe I'll go look over at the tooth that I'm interested in. So now that I've done my due diligence on the rest of the teeth, now I'll probably pop over to oblique slicing. And again, now you can really clearly see there's something going on over here, right? Okay, so let's look at the tooth of interest. Lower first molar. What do you guys see? What do you think's going on here? And we can change our slice angles as well. Any guesses? Yeah? Vertical fracture. Everybody thinks it's a vertical root fracture. What makes you say that? You sure? How reliable is this finding right here? Semi. I think semi is the right word. So again, I didn't describe anything about the case, so this is actually how you do cone beam CT research. Did I tell you anything about the case? I mean, you saw initially that there's a finding on that tooth, but we don't know what her presenting complaint was. We don't know anything. We don't know what the periapical radiograph looks like. We don't know any of those things. So we're not rolling into the task with all of that prior information. This is a strict interpretation task of just the radiography. You can't do a burr hole drilling project knowing that you're doing a burr hole drilling project and get the slices lined up right on the burr holes and then ask about the burr holes. It's too task specific. We're really good at that. What we're not so good at is finding the needle in the haystack. We missed that, yeah.
That means that you want to do your exam without any clinical information?
No. What that means is that you want to, as you're doing this radiographic interpretation task, especially now as we're learning to it, you want to suspend, you want to pretend as if you didn't have that information and look at what this actual evidence is. And this is, again, what we talked about yesterday at length, is separating your prior information, the prior probabilities, from the evidence, because the cone beam is a separate piece of evidence. And if you look at the cone beam with a knowledge of a vertical root fracture or a suspicion of a vertical root fracture, you're far more likely to interpret it that way. And then if you load your data set that you're doing a study on with 75% of the cases already having had a vertical root fracture, well, how good does the cone beam need to be to find them? Not so great, okay? So you want to look at this cone beam now in a sense that, I wonder what information this cone beam gives if I didn't know anything about the case. And the answer is, yeah, it looks a little funny here, and it looks like it might be a fractured root on this tooth. But can we really see the fracture? No. You can maybe see some indirect evidence of it that looks somewhat organic here. Now, what about the dark spots here? That came right from, and if we look at it, if we zoom out, so this is the good thing sometimes about not looking at things too closely. You can actually see the lines connecting all of the gutta percha in the case. Mitch has a wonderful example of this that I'm just not going to have time to show, where it goes from 1 to 1 to 2 to 1 to 2 to 1. You can see the reconstruction artifact going zigzagging like this all the way through. I'll see if I can get this one lined up to do that for us. But if you look at it from, say, 50,000 feet, you can see reconstruction artifact connecting all of the gutta percha all the way through the length of the mandible in that direction. You don't want to do an interpretation around that, but you almost need to look at it from a distance, because if you look at it close like that, you won't see it. You're zooming in on it too much. Get it? Yeah. So you want that 50,000-foot view of the case to kind of grok it, to kind of get it. And then you want to look everywhere else first, because gutta percha acts as contrast. And if you look there, you may miss other findings. Scott, have we done that? Yeah, it's very embarrassing when Scott looks at my case and says, there's a peg lateral, and I missed it. Or I looked at Scott's case, having some prior information and going, the central incisor's cracked, because I had the RD call and tell me it was cracked, and I knew exactly where to look, and I found it. That affects your ability to interpret the images. Scott missed it because he didn't know it was there. I found it because I knew where to look. He found and it was the same case where I went right to the crack and I missed the peg lateral. And Scott saw the peg lateral and missed the crack. Same case, okay? So, back to oblique slicing. So you want to look at it kind of in a zoomed out kind of way and look at those overall patterns of the reconstruction artifact and try to figure out where things are going, how the waves are overlapping, and then over here is the dental implant. I think I got a slide for that. So I'll just show you that case. Yep.
When I look at a cone scan, I don't look at it until after I've done everything as far as examination.
Great. Yep. Yep.
That's what you're saying you should do the other way?
Yes and no. When you're doing cone beam research, you must remove the clinical information because the clinical information colors your interpretation. It's been well studied in medicine, and Birbaum's done some of that work as well. And having the clinical information does improve your interpretation task. But if you're studying cone beam as a device, you can't have that information. As a clinician, you can't avoid having that information because they came into your office, they've got a complaint, and you can't get that out of your head. But what you can do as you're thinking about the image is think, if this person didn't have a probing and didn't have a complaint and didn't have anything going on and wasn't in my office, how would I interpret this image? If we subtract out that, we have to take specific cognitive steps to, in ways, subtract out that prior information that's coloring our interpretation task. That's very difficult to do. So that's when you hear me say, the findings on a screening type of examination, when you're just looking at things, the findings need to be clear and compelling for us to move, because the prior probability is low in a screening situation. Is all this stuff starting to tie together now? Okay. When you have the patient in your office and you're doing the examination for diagnostic purposes, it's a different situation because the prior probabilities are different, because they may have a probing and they may have a complaint, and that elevates the chances of them actually having a problem, and that elevates the chances of the findings on the cone beam CT being actually real. But as you're interpreting the cone beam CT, you kind of want to switch back and forth between those two things. If I didn't know all of those things, how would I interpret this cone beam CT? And I'd go, well, maybe that little C-shaped radiolucid, maybe that's a finding. I'm going to go look there. And so I went and looked there.
So
Guess what?
To look at this another way, if you think about when you're looking at a cone beam, if you could kind of understand what is the natural rate of type 1 and type 2 errors that you are likely to make. And if you are aware of the kinds of errors that you are likely to make, then when you look at the clinical, the priors that you have, you will be much less likely to make those errors, having known what the natural rate of type 1 and type 2 errors is with this technology. That's the way that I would look at it.
Sure, yeah. You guys have all seen my posts, and I'm a late treater. I wait. I feel like in healthcare generally, we make far more errors of commission than errors of omission, and we hurt a lot of people. And we do a lot of unnecessary testing, and we cut a lot of people. And that's where you don't need to be a great cancer surgeon to cure a patient with no cancer comes from. So I tend to be a late treater, and I'm willing to miss something and then and then pay the price rather than do something to someone that I know is going to have a biological price. So it all depends, and this is right back to Birbaum. It depends on where your decision criteria is. God, I wish we had more time, Gary. Because what they've done with medical radiology, and a study came out about 10 years ago, is they looked at about 100 radiologists, and there's this huge scatter plot in sensitivity and specificity between these radiologists. Some of the radiologists' sensitivities, these are mammographers. Their sensitivities and specificities range from 0.1 to 0.9. 0.1 to 0.9 for expert mammographers interpreting mammograms. 0.1 to 0.9. What does that say? It's all over the place. What does that mean? It means, not necessarily, it means they're operating at different points along that ROC curve and their willingness to make the call. Some guys, like me, are more concerned about false positives, telling someone they need treatment when they actually don't. I can wait. If they need treatment, they'll be back. Okay? Worst going to happen is going to hurt. We talk about all that. Other people are like, oh, you got to retreat this. There's a lesion. Nishan? There's a lesion. You got to treat this. So you're going to make errors. It is unavoidable. It's impossible to bat 1,000. You just can't do it. So you got to give that idea up, that you're going to bat 1,000. You're going to make errors, and like Gary said, you got to decide where you want to be, and you got to understand the nature of those errors and what kind of errors you're willing to make. It's that whole sensitivity specificity bit. Here, I went back, and I had the cone beam information, and I looked at the case. Here's the preoperative radiography on the case. The girls covered the area. Thank you, girls. And I looked at this, and it's like 10 years old, and it's kind of chubby, and she's missing 19 and 20 already. They're both dental implants, 10 plus years. And I looked at this, and I said, this is fractured. So that's my prior probability there. We ran the cone beam just because I'm interested in seeing what these things look like. So you're going to take a lot of cone beams just to see what these look like. How do you get good at this? You take a lot of cone beams. It's the only way to do it. Is there another way to do it? No. If you're reading 6 cone beams a year, you will never, ever be any good. Ever. Ever. You need to read hundreds. And the medical radiology community study this. It's 10 to 20 years. It's 20 years to become an expert mammographer. It's 20 years with feedback. So I looked at this and I said, this is fractured. Besides, it's not a great retreatment candidate. Anyway, it's hog. She's got successful implants. She likes that. I'm not even talking about that. I'm going to look for a probing on this tooth. What the cone beam did is it told me, why don't you go look here? Why don't you go look here at the ML? So we went and looked at the ML and got the plaque cleared off. And we've got a little badip right there, a little fracture. I mean, it's teensy. I probed. Why? To take a picture? No, to take a picture. Yeah, that's it. I probed it to take a picture. That's it. Yeah, this is Monday, so I wanted to show you like a case from Monday. This is how we did this case, how I did it. And sure enough, 2 implants, right? Are those in the field of view? No. Can you see the 2 implant artifacts? There's a trace there and a trace there. Get it? What kind of artifact is that? It's a reconstruction artifact. Where are the dental implants? They're over here. They're outside the field of view. Things that are outside the field of view can affect things that are inside the field of view. Our eyes play a lot of tricks on us. I got to call it there. I didn't get anywhere near what I wanted, but I never do, but it's still all good. I hope we got those 3 kinds of things identified and see how they can interact. It's pretty interesting stuff. Thank you, guys. I know we mushed through.